So we're talking specifically about the rusting of iron. What physical conditions is required for rusting?
Water and air.
Water and oxygen, yeah. And there's a half equation on your electrochemical series that I said that you need to make sure that you can always find and highlight. Can somebody tell me what it is? That one? O2, is it?
Yeah.
How many orders? How many? 2 electrons?
No, carry on.
Plus 4 electrons.
I'm only
Sorry,
interested
I'm
in the half
looking- yeah,
equation at the moment. And what do we produce? 4 hydroxide ions. So it's really important that you can identify, find this equation. This one happens for all corrosion. Okay, this is the reaction at the cathode. And as we saw on the nail, we were producing hydroxide ions at the cathode on the nail. We can't reduce the ion any further than it already is. It's already Fe. Okay, so how can we add more electrons? We can't. So we cannot reduce the ion. But what can happen is that on the surface of the ion, we are then able to reduce the water and oxygen that's in that local environment on this surface.
So my Fe is the cathode.
The Fe acts as the cathode, yes, upon which this reduction reaction occurs. Okay, so the metal here is the cathode. It's also the anode in the rusting of iron. In that nail, we had oxidation and reduction occurring on the same nail, didn't we? So what we're trying to do is find the locations where we are likely to find the anode and where we are likely to find the cathode. And so these ones will come down and react onto that surface, and hydroxide ions will come off. All right? So that's why this is a really important half equation, because this is going to be what you need to look at every time you're looking at a corrosion reaction. Now for our iron, yes, we have Fe going to Fe2 plus, that's 2E minus, and this is then oxidation of iron. And if we look at where on a surface is this likely to occur, and if this is our iron, and you get, like it could be your car, we talked about some people having a bit of rust on their cars last lesson. It could be a scratch, it could be a little dent, it could be just a spot where the water pools often. But there's some little imperfection, and this is where the rusting will start. Okay, so a small scratch or something like that. And what will happen is that over time, it will be able to collect water. And that gives us an environment that is rich here in oxygen and water. And what we tend to find is, and this will grow bigger, so let's draw a bigger depression now so we can, or maybe we'll say it's the same depression, but now we're zooming in, looking at it in more closer up. So if I have water in this little depression, this is water, it's this interface here. It's this interface here, which is the rim, if you like, of, if this was a circle, a dish, and this is the outer rim, is where there's the highest concentration of water and oxygen. And if you have a look at this, just this tiny diagram in your booklets, and I've got a better one that I'll copy for you, and we can have a look at. This is then the location of the cathode. And our anode is under here. Now, it might surprise you to realise that the anode is actually in an area where there's lower oxygen. Because we think, oh, oxidation at the anode, we sort of think oxygen must be around. But oxidation is going to occur where there's less oxygen.
Is where those points go down, is that a stress point?
No, the reason why it happens here is simply because this is where we've got, so in this little corner here, we've got a combination of oxygen and water present. That's the highest concentration of both of them, and we need them both present. Yeah. This, I guess, if you like, the scratch or whatever can also be thought of as a stress point. But even if we had a perfect sheet of iron that had no imperfections, if we leave it out in the weather, it will rust. So eventually we'll find some imperfection on there for it to start. But the anode is going to be where there's the lower oxygen around. And we've got less oxygen because that water is preventing the bottom of this depression from having access to the atmosphere up here. Okay, so yeah, we're thinking here is our piece of iron. This is the air. And we've got water in that depression there. And so it's on these edges, this is where the rust will actually deposit on the outer edge of the rim. As the iron will oxidize and makes its way over to this area where we're forming the hydroxide ions. They will come together to form the iron hydroxide, and then our rusting process begins. Okay, so the cathode is all around the rim. I've only labelled it on this one part here, but all around the edge of where the water is pooling is the cathode. And all of the area underneath the water is the anode. Now we can see that our ions are going to be able to meet up together in this little puddle of water, because I've got iron ions here and I've got hydroxide ions that are forming in this area. But our electrons travel through the metal. So if we look at that, our electrons are going in this direction up here from the iron that's being oxidized up to the cathode, so that this reaction can proceed. So the electrons must travel through a conductor. They can't travel through the water or the air. They're going to go through the metal. Do you remember once we formed our iron hydroxide, do you remember what the next step was? Further oxidizers. And then
Dries
to
down. Same thing, but relation.
yeah, we have to remember our waters as well, because if we look at that, we've still got hydrogens there, haven't we? So that's why we don't exactly know how many we have, but we need to include that it's a hydrated iron oxide. Now, what do you think is going to accelerate? What kinds of environmental conditions will accelerate corrosion rates?
Solid wood.
Okay, yeah, but Georgia?
Just temperature?
Yeah, so if we think about increasing the temperature, what does an increase in temperature do for the particles that are present?
Makes them move quicker.
Yeah, so that we've got an increase in kinetic energy of the particles, and therefore they will react faster. So that would mean an increase in temperature would result in an increase in rusting, wouldn't it? It's going to happen more rapidly. And conversely, if we decrease the temperature, we can also decrease the rusting. What now? Mason mentioned salt water, which is absolutely right. What does the salt water do for us? Why would things rust more rapidly in the presence of salty water than in the presence of pure water? Yes?
Does it make a salt bridge?
Well, yeah, it's sort of like a salt bridge, yeah. Salt water, the salt, we can call that electrolytes. And it is functioning in the same way as a salt bridge in that we know that our ions can carry charge, yeah? And so these, if we've got charge carriers present here in our little puddle of water, then this is going to all happen a whole lot faster. Pure water is actually not that good as a medium for redox here, because for our ions need to move, and in pure water that's harder to do than in the presence of some electrolytes. What else?
Just there being more humidity and more water around, because there'll be more puddles like that forming.
Yep.
If it's very dry, there won't be any water.
Yes, we need both. We must have both, and therefore a humid atmosphere is going to increase the rate of rusting. And so that would mean that if we're comparing somebody's car who lives, in, I don't know, Singapore or the Philippines with somebody who has that same model car who lives in South Australia, both warm climates, but South Australia is very dry, we would expect to see less rust on the car in South Australia than we would in say, the Philippines. We have to look at all of the factors together though, because if the person in South Australia lived near the beach, then even though it's dry, they're going to have high salt content around, and the moment it rains, they're going to have a high concentration of salt on their car if they don't wash it a lot. People who live near the beach should also really wash the pot underneath their cars, because that can be a spot where rust starts and you're not aware of it. Yeah, and the same then for availability of oxygen. So if something is in a lower oxygen environment, then it's less likely to rust. Can you think of where a lower oxygen environment might be? Sorry? Up high. So really up high, you know how most of our atmosphere is quite close to the land, and as you go higher and higher, there are less and less air molecules, and so So rusting would be very difficult because we wouldn't have any water or oxygen up there. However, we don't have a lot of stuff up there. Where is another location?
Like places with high pollution.
High pollution?
Yeah, less oxygen.
Look, they probably still have enough oxygen to breathe, so they're going to have a lot of other things in the atmosphere, but that's a good thought.
If you paint your car and put paint and cover it so oxygen can't get to the iron.
Okay, so yeah, good idea. And so a barrier. Grace? Underwater, that's where I was trying to head. If we think about things like the Titanic, you know, when the Titanic sank, and it ended up going 4 kilometres to the bottom of the ocean. In fact, I think it's in the Mariana Trench, isn't it, which is even deeper than 4 kilometres. And so that means that it's a low oxygen environment. It lasted a whole lot longer because of that. I mean, it's quite fragile now, it's pretty old. But it was underwater intact for decades. Even though it's made of iron and you know, it's in the presence of all that water and all that salt. There are 2 things against it rusting: low temperature and low oxygen. And so this is why we have to think about them all together. But this is a good idea here in that for us in our everyday lives, where we're using metals a lot, and we don't want to, you know, fill our air with pollution, or we don't want to sort of start living underwater or whatever. We need to be able to protect our iron in those conditions where we are living. A barrier is one way of protecting the iron. Now, if we think more about barriers, what kind of barrier could it be? No idea?
Well, there's also different like coatings and stuff for protecting iron from
A coating. Yeah.
Another ionic compound? If there's another metal in the iron? That's how, like, stainless steel works, isn't it? So it's like
yeah,
chromium oxide on the outside?
That's an alloy, and we don't really talk about alloys in this course. With an alloy, your product will take on properties of what, you know, a combination of what you've got in there, and so chromium steel, for example, doesn't rust like iron does because of the chromium present. Yeah, okay, a coating. It could be like paint. It could be something like oil or grease. It could be a plastic coating. Those sorts of things are going to be a barrier, aren't they? And we can use all of them. Now, we haven't quite finished going through all of the factors that are causing our corrosion. If we think back to our bent nail, stress and metal fatigue is going to be another potential cause. And the contact between 2 metals. So we'll think about this in a few moments. But, and the surface area. So just, if we've got a large surface area exposed, we can expect that we're going to have more potential sites for this to occur, and so there'll be more rusting. If there's only a little bit of a surface exposed, then it's going to be less likely to rust.